Hi folks, welcome to M371. This is elementary computational methods, or sometimes just referred to as numerical analysis. So this is about using computers to actually compute numerical answers to mathematical problems, right? So typical sorts of applications will be for finding roots of algebraic equations, calculating integrals, calculating derivatives, right, and doing all those things using purely numerical methods, not attempting to get the exact answer, but just trying to get an answer that's accurate enough for practical purposes, right? So there are a lot of things in mathematics that, in principle, they have exact answers, but the exact answers may be too hard to figure out. They may be too cumbersome to be practical. And it may be that it's better just to use a computer to approximate solutions. And that may be good enough for practical purposes. Okay, so we're going to be using the math package Matlab in this course. If any of you were with me in mathematical modeling, 447, I used Mathematica in that previously. I probably will not be using it again. Matlab is actually better in a lot of ways. Well, first of all, it's designed for number crunching rather than symbolic processing. So Matlab is good, is the ideal platform to use for this particular course where we're doing numerical computation. And in fact, Matlab is also basically the industry standard for doing number crunching in the sciences, right? So in chemistry and optometry and biology and in physics and in math too, Matlab is used to do numerical calculations. One advantage of using Matlab at IU is that IU has a license where all students can download it to their own computers and run it on their own computers, right? Which is much, much better than the situation that some of my former students had to endure with Mathematica, where we had to run it on IU anywhere. To get Matlab, if you haven't already, follow these instructions. Go to iuware.iu.edu. Notice this is IUware, not IU anywhere. This is one of the advantages, a great advantage of Matlab. You don't have to run it on IU anywhere, which is a very awkward platform. You can actually get it from IUware and download it and run it on your own computer. You'll find it under the analysis and modeling category and select Matlab. You may have to select your operating system, Mac or Windows or Linux. It's available for all three. What you do is you use your IU login to get a license, right? So it'll issue you a license. This will not cost you anything. As I said, IU has a deal with Matlab. And then you can download the installer. And when the installer is downloaded, you run that. At some point, you have to verify your IU identity and maybe enter your license number and things like that. So be prepared anyway to log in to IU, using our Duo system. And also be forewarned that it's a large download. It can take, I think it takes at least 30 minutes, and it could take an hour or two depending on your internet connection. Right? I made the terrible mistake the first time I taught this course of having everybody try to install it the first day of class, and almost no one was able to actually finish the installation during class itself. So do that outside of class, and then get back to me when you've done that, and I'll continue with a brief introduction to how Matlab works. Okay, so once you get Matlab running, it looks something like this. For the moment, we'll be focusing on the command window over here. There'll also be a folder window. It'll show you files in the current folder. By the way, you can change the current folder by clicking, let's see, I think that this one allows you to browse to a new to a new folder. Yeah. So I happen to have a Matlab folder set up in my M371 directory. So you'll probably want to do something similar so you can save your files in a convenient place. Let's see. Also, there are different layouts that are possible. There's a little button here called the layout window. You can select different kinds of layouts, two-column, all but the command window, and so on. And you can customize exactly what you want to see. So you can experiment with that. It depends on what kind of monitor you've got, what kind of layout you want to set. But okay, let's look in the command window, and this is where you can interact with Matlab. And so you can do things like you can add 1 plus 1, right? And the answer is 2. You can take 235 raised to the 47th power, and it'll do that for you. It's 2.755 times 10 to the 111th power, right? If you don't want to see the output, you can put a semicolon after it to suppress the output. A common time to do that is when you're assigning variables. You're assigning a large value to a variable. You don't really want to look at it. You can introduce variables very easily. You just say x equals. So I can say x equals 235 to the 47th, and maybe I don't want to look at that output. I just want x to store that value. I can put a semicolon, and now there it is, and if I evaluate x, it'll give me that value. Of course, you can do subtraction, 23 minus 11. You can do division. You can do 257 divided by 200, right, whatever. Let's see, notice that you do have to use, I don't think I did multiplication yet, but you have to use the star for multiplication, so, right. And what else? Oh, one thing that's quite useful is sometimes you want to switch the format of the output. So currently it's set on a long format where it prints, let me see, what is it, about 12 places? No, how many have I got here? 1, 2, 15 decimal places. So if you want to see less of the numbers, what you can do is you can type in the command format with the qualifier short and enter that, and now when you view things, for example x, it'll only show you 4 decimal places, right? So that's sometimes it's inconvenient to see too many decimal places. It takes up too much room on the screen, right? So you can switch back and forth depending on what's convenient. If you want to go back to long format, you just type the command format long, and now it'll type everything in 15 digits. Let's see. It has all the usual built-in functions. So, for example, sine of pi over 2 is 1. That's right. So note that the trig functions are all by default set to the radian mode, right? So you enter the angle in radians. By the way, pi is a built-in constant, right? So you can just type pi, that's pi, and you get the value of pi. There are other constants that are built in. I think pi is the only one we're really going to use. If you need to use e, you call the exponential function. So if you want to raise e to the second power, you call it exponent of, or the exponential function of 2, right? That's e squared, right? If you want to get the value of e, you can just call the exponential function with an input of 1. That would be e to the first power. And this is e, 2.718, etc. Let's see, it's got the inverse trig function. So, for example, a sine. So that's short for arc sine, right, or inverse sine. So a sine of 1, that should give me pi over 2. Yeah, and that is pi over 2, right? And it's 3.14159 divided by 2. Of course, it gives you the principal value of the arc sine function, so it gives you a value between 0 and pi, or between negative pi and pi. Oh, let me see, what happens if I take arcsine of negative 1? Then it gives me negative pi over 2, right? So by default, it gives you a value of theta, of the angle between negative pi and pi. What else? Let's see, it's got the log function, log, so log of 2. And by the way, this is the natural log. We're never going to want to use the common log anyway, and it's seldom used. So log means the natural log base e. Right? So for example, log of exponential of 1, this should give me, let's see, exponential of 1 is e, log of e is 1, so this should give me 1, right. Let's see. Other useful functions are the floor and ceiling function. The floor function just cuts a number down to the smallest integer, not exceeding the input, right? So like floor of 2.3 will be 2. Only thing slightly confusing about this is that if you apply it to a negative number, it gives perhaps unexpected results. A floor of negative 2.3, well, the smallest, the largest integer not exceeding negative 2.3 is actually negative 3. So that's what the floor function does. It goes down to the first integer not exceeding the input. Ceiling does kind of the opposite. It takes the smallest integer not less than the input, right? So ceiling of 2.3 would be 3. That's the next integer up. And again, it seems perhaps a little strange at first, but the ceiling of negative 2.3 would be negative 2, because that's the next higher integer, right? Incidentally, you can go back and forth between commands that you've entered earlier by using the up and down arrows, right, on the keyboard. So that's very convenient. You can easily recall an earlier quantity that you evaluated, or a command that you evaluated, even make a slight change in it, and then reevaluate it, right? Very convenient. I mentioned that you can introduce variables, so I can say x equals 1, y equals 2, and you don't have to declare them, really. If you're coming from computer science, Matlab is not exactly a highly type language. I mean, everything does have a type, but it's designed so that you don't have to worry about typing very much. And so you can just introduce a variable by simply setting it equal to something, right? You don't have to declare its type. You can declare the type if you want to, right? But usually the default types are perfectly adequate for what you want to do. Let's see. And then you can do things like x plus y, right? And you can evaluate that. What else? There's a very useful rand function that returns a random real number between 0 and 1, right? So every time you evaluate it, you get a different value between 0 and 1. So that's really useful for simulating random processes. Let's see. Another thing, it has a pretty good built-in help system. So if you type help in the name of a function or something, so help on the floor function, it'll tell you exactly how it works, what the inputs are to the function, what the output represents, and things like that, right? So keep that in mind. If you're ever confused by something, try the help command to get help on a function. There's also, I think this little question mark over here will take you to a dedicated help page, right? And that can be helpful, yes. Okay. Let me go back. I'm going to talk about some basic control structures. This course is not really a course in computer programming, but we will use some basic computer programming concepts, right? So, and the only ones we really need are the basic control structures, that is conditionals and loops. So let me talk about that first in the slides, and then I'll come back to MATLAB. Okay, so There are two kinds of loops in Matlab. There are for loops and while loops. If you haven't learned computer programming, don't worry. I'll explain everything. They're very simple. For loop is used in situations where you want a variable to go through a series of values, perform some operation, and then go to the next value and perform the operation again, and so on. Right? So as a really simple example, here's a for loop where x will take the values 1, 2, and 3. So I say for x equals 1 colon 3. So 1 is the starting value, 3 is the ending value. By default, on each iteration, the x value will increase by 1. You can change the increment. There are ways to do that. Actually, you put a third argument in the middle to change the increment. And then each time, for each x value, it'll calculate x squared, and then it'll go on to the next x value. Right? So this is a very simple loop. Right? So if I run this, by the way, you can type this in. In fact, try it. Type it in at the command line in Matlab. When you type the first line, Matlab will know that the command is not complete. So when you hit return, it'll wait for more input. After you type the x squared, it'll still wait for more input, and it won't know that it won't realize the command is finished until you type end. Right? That ends the for loop that began on the top line. So, but by the way, in Matlab, most multi-line commands have to be terminated with an end statement. Right? So a for loop and if-then statements and things like that all have to be terminated with an end statement. Okay, so you can just type this into the command line, and then when you enter this third line here and hit return, it realizes you've entered a complete command, and it will perform the loop. So when x equals 1, it computes 1 squared and prints that out. When x equals 2, it computes 2 squared, and when x equals 3, it computes 3 squared. Okay, and it'll type all those values out. If you don't want to type the value each time through the loop, you can put a semicolon over here. Okay, and you may not want to do that depending on what you're doing. Okay, let's try this out, because for loops, as simple as they are, they're very powerful because they allow you to do things many, many times very, very easily, right? So here's an example from, you may have seen this series in calculus. This is an infinite series expression for pi over 4 that was discovered by Leibniz in the 18th century. It actually comes from the power series expansion of the arctan function, right? You take arctan of 1. But anyway, the series says that pi over 4 is equal to 1 minus 1/3 plus 1/5 minus 1/7, so on like that, alternately adding and subtracting 1 over the next odd number. You can write this out in series form this way. I goes from 0 to infinity. In the numerator here, I have -1 to the ith power, so that the signs will alternate. When I is even, this will be adding, and when I is odd, we'll be subtracting. Right? And the denominator is the sequence of odd numbers, right? So when I is 0, this will be 1. When I is 1, this will be 3. And when I is 2, this will be 5, and so on, right? So we go through the sequence of odd numbers. It'll be more impressive if we can get this to just spit out pi. So what I'll do is I'll multiply both sides by 4, so we can say that pi is equal to 4 times this sum. Right? Okay, so this is going to be really easy to do in Matlab. All we do is we say, well, first of all, I'll start off with by initializing the sum to 0. Right? What I'm going to do is I'm going to have p represent the sum of the series. I'll start it off equal to 0, and then I'll create a loop, a for loop, where I will go through the values from 0 up to some large number, and on each time through the loop, it'll add the current value of this expression into the value for p. Okay, so we start off with p equals 0. As I said, I'm gonna do it when I goes from 0 to 1,000, right? So even Matlab cannot do all infinitely many cases, but going from 0 to 1,000, that should give us a pretty good idea what's going to happen, and we should get reasonably close to pi that way, right? So we'll have I goes from 0 to infinity, to 1,000. Each time through the loop, what we'll do is we'll take the old value of p and we'll add to it, so p equals p plus, And then what I've got here, this is exactly the MATLAB expression for this summand over here, right? So we take minus 1 raised to the I divided by 2 times I plus 1, right? And here I did put a semicolon at the end of it because I don't want to print out all 1,000 intermediate values of p, right? I don't need to see all of those. And then type end to complete the for loop. MATLAB will evaluate this loop. It'll go through all 1,001 values of I, and then finally just evaluate p to see what the value of p comes out to be. And you can see that it just going from 0 to 1,000, we got a pretty good approximation for pi that way, right? Pi, we got 3.14259, right? It's a little bit higher than it should be. It should be, was it 14159? But it's pretty close. Let's see. By the way, this is a pretty cool formula for pi, I think, right? For pi over 4. However, it's not a good way to estimate pi. So sometimes you'll see news stories about people who ran a computer for 3 weeks and calculated pi to like 1 billion decimal places. They don't use this formula. This formula is very, very inefficient for actually computing pi to a large number of decimal places. But it is cool because it's so simple and it's so kind of natural and easy to remember. And it does work. It does give you pi. Okay, there's one other kind of loop that will come in handy this semester, the while loop. And this also loops around and performs an operation repeatedly, but instead of always incrementing a certain value, it works by checking a condition. So if the condition is true, it'll keep executing this command, and then once the condition is false, it'll break out of the loop. It'll stop executing it. So as a simple example, I'll start off by setting the value of x equal to 0 over here. And then we'll check whether x is less than 10. So the command while x is less than 10 has the computer check whether or not this condition is true. If it is true, it will go on and execute the next command. If it is not true, it'll exit the loop, right? And the loop consists of the lines from the while until the end statement, right? So while x is less than 10, it'll increment x by 1. It'll actually increase x by 1 each time, right? It says x equal to x plus 1. So of course I could have done this with a for loop, right? But I just wanted to demonstrate how the while loop works. And then eventually, of course, x will go from 1, 2, 3, all the way up to 10. And when x finally reaches 10, then this will no longer be true, and it'll exit the loop and stop looping. Right? And then if you evaluate the x value, then you get x equals 10, right? Because that was the value at which the loop stopped executing. Right? So try typing this into MATLAB, make sure it works. And just a simple example of how while loops work. And then as a more practical example, something that's actually a little bit useful, we can use a while loop to simulate a geometric random variable. So a geometric random variable is, for example, the number of times you have to roll a die until you get a 1, for example, right? You take a fair 6-sided die, and you keep rolling it until you get a 1. You count the number of rolls before you got the 1, right? Of course, you might get the 1 right away, in which case the number of rolls before you got the 1 would be 0, but you might, it's very unlikely, but you might have to roll 100 times before you finally get a 1, right? So a geometric random variable can take any natural number as a value, right? Anything from 0 to infinity. But of course, they get increasingly unlikely for large numbers, right? Very, very unlikely you'd have to roll a number more than like 12 times before you get a 1, right? Okay, so how do we simulate this in MATLAB? Oh, by the way, by simulate this, what I mean is we'll have some code that when we execute it, it'll just spit out a random number that has the same probability distribution as a geometric random variable, right? So it could have been the number of rolls before you rolled a 1. Okay, so that's easy. We can simulate rolling a die by taking a random number. Now remember, this rand function generates a random number which is uniformly distributed between 0 and 1. So that means 1/6 of the time the number will be less than or equal to 1/6, and 5/6 of the time the number will be greater than 1/6. Right? It's a uniform distribution between 0 and 1. Therefore, if I check the condition, rand is greater than 1/6, this will be true 5/6 of the time. And that is exactly the probability that with which you do not roll a 1, right? Every time you roll a die, you have a 1/6 chance of rolling a 1. That means there's a 5/6 chance you did not get a 1, and you have to roll again. So rolling again means that we have to, repeat the loop. We have to execute the loop one more time. Finally, when we get a random number that's less than 1/6, or less than or equal to 1/6, that's equivalent, we can think of that as like the event that we finally rolled a 1, and then we can stop the loop. Every time through the loop, we increase this counter that we have by 1. So we start the counter off at 0, right? Before we started rolling the die, the number of die rolls is 0. Every time through the loop, we increase that counter by 1. So n equals n plus 1. And then at the end of the loop, when we finally rolled a 1, n will have the total number of rolls that were required before rolling the 1. Right? Now in this case, we got lucky. Apparently we rolled a 1 on the very first roll, so n was 0. But every time you execute these lines, you're going to get a different value for n, right? Because the random numbers are going to be different each time. So the next time I did it, we had to roll 2 non-1s, and then finally we got a 1 on the third roll, right? And as I said, if you keep executing this, you'll get different numbers, each time, potentially different numbers each time. They can sometimes be large numbers. They can sometimes be 10 or 20, but that's kind of unlikely. Next thing we like to do is talk about how we could make this a little more convenient to run pieces of code like this, right? Having to type in these 3 lines over and over again every time you want to simulate a geometric variable is obviously very awkward. So there's a way to write these into scripts that we can execute more easily. Okay, so how do we make a script that we can run more easily? What you do is you can select the New button. And this will create a new file that you can work on. So we'll select New Script. Okay, notice that it opened a new window, an editor window, where you can edit the file. And then we'll also have a chance to save it later. What I think the first thing you should do, good idea to get in the habit of commenting your code, right? Providing documentation for your code. So I'll just say what this is going to do. This is going to simulate a geometric distribution, or geometric, let's say random variable, and with, let's say, in this particular case, with p equal to 1/6, right? So in general, geometric random variable takes a parameter p, which represents the probability of success. And then the geometric random variable, the value of the geometric random variable represents the number of trials that were necessary before achieving the first success. Okay? Oh, and by the way, the percent sign at the start of the line means that these are comments and will not be executed, right? So use these percent signs whenever you want to remind yourself of how your code works, right? You can just put in a comment with that. So we'll say, let's see, now the first thing we wanted to do, now we can start entering the commands. We wanted to say that the number of rolls, will initialize it to 0, right, initially, n equals 0. Put a semicolon in because we don't need to print that every time this script is run. And then we'll do a while loop, while this random number is greater than 1/6, right? That simulates the situation where we rolled a number bigger than 1. We haven't gotten the number we wanted. Then we have to increase n by 1. N equals n plus 1. Again, put a semicolon, and we don't need to print out that value each time. End the loop. When the loop is ended, when it's exited, that'll mean that the random number that we got was less than or equal to 1/6, and that simulates rolling a 1, right? So at that point, we can simply print out the value of n, and that'll be the value for the geometric random variable. Okay. Let's see. Let me hit the run command. You notice up here there's a button, looks like a play button on an MP3 player or something on your phone. Just run that. Oh, we have to save it first, right? So find a good place to save it. Find an appropriate folder where you can find things easily. And I'm saving it in a temporary folder, and give it an appropriate name. So I'll call this, I don't know, GM Rand. How about 6? Because this is simulating a geometric random variable for a 6-sided die, right? Ah, there we go. Okay. So it executed it. If I press it again, it'll execute it again. I get a different number for n, right? Different value. And at that time it was exactly the same. But in general, you're going to get different values every time you press the play button on this. You can also execute it simply by typing in gmrand6 at the command line, right? Oops, rand6 at the command line, and execute it. And just keep executing. It's actually easier than pushing the play button, probably. Right? Now, that's nice. Something that might be even nicer would be if you could simulate rolling a die in this way, but for a die with an arbitrary number of sides, so a number of sides which you specify, right? So, in some games you roll 4-sided dice, or 10-sided dice, or 12-sided dice. So you might want to be able to simulate dice of any size, or random numbers, random number generator of any size. So what we could do is, now let's see, I think what I'll do is, let me copy this, and I'll start a new file, and I'm going to use most of the same commands, but I'll, so let me, what I can do is now I can hit the plus button. Notice up here in the editor there's a little plus button. I can hit the plus button to start a new file, and I'll type in or paste in the commands from before. But now what I'm going to do is I'm going to want to make this into a function in which we can plug in the number of sides, right, for the die. So, for example, in the version we just did, it was modeling a 6-sided dice, so the number of sides would be 6. But we'd like to generalize that so we can give it any number of sides and have it produce a geometric random variable, right? So to do that, what you do is the first line has to look like function. Function. And then, now this is a quirk of Matlab, which I think is a little bit weird, but we can get used to it. You type in the value that's going to store the output value. So function n, because the output of this function is going to be n, the number of times we had to roll the die. And then we say it's equal to, and now we have to give the function a name. And by the way, the name will have to be the same as the file name when we save it, right? That's an important thing about functions. The function name has to match the file name. So I should make it something a little different from gmrand. Maybe I'll say geom rand, rand, how about n? Because this is going to take, an input. How about rand s? I'll give it an input s. And so on the right side of the equal sign, we have what the function looks like basically when you call it. We're going to call it as geomrand_s, and then the input is going to be the variable little s, and little s will represent the number of sides. So I'm going to alter the comment here. I'm going to say that the p is not equal to 1/6, but it's equal to 1/s, right? So s represents the number of sides. So what we're doing here is we're simulating a random variable, or we're simulating a die that has s sides, and therefore the probability of getting the particular number that we want is 1/s. And I'll also change this 1/6 to 1/s here. right? Also, a function will automatically return the value that we specified here, right? This is going to be the return value, so we don't need an extra line that prints out the value, right? I can leave that off. You can, I don't think it's necessary, but you can also put an end statement for the function. So this ends the function statement. Okay, so the first end is for the while statement, and the second end is for the function statement. Oops. Although I don't think that second end is actually important. I don't think you'll confuse Matlab if you don't put that in. Okay, let's save this. It'll ask me for the name, and yeah, and by default, it'll try to save it under the name of the function itself, and that's what we want, right? So we'll save it under that name, geom_rand_s. And now what we can do is we should be able to run the function by typing in geom_rand_s, and we'll give it a number of sides, like how about 10 sides if we're rolling a wait, do we have 10-sided dice? How about 12 sides? Yeah, like a dodecahedral die, right? Okay, so that time it took 4 rolls to get a 1. Let's do it again. This time it took 50 rolls. Wow. Well, that can happen if you have a 12-sided die. It can take a large number of rolls before you get a 1. Let's do it again. Ooh, got it right away. Right. So anyway, so this is seems to be working correctly. It's giving the right kind of variety of values as outputs. Okay. So anyway, that's how you make a function. So this will be quite useful. Another quirk about Matlab is that each function has its own file. So you don't have a single file that contains lots of function definitions, but you have one function per file. It's kind of a peculiarity of Matlab. And we'll be doing this a lot throughout the semester, right? So that this is going to be our kind of a basic unit of code will be these function definitions throughout the semester. Okay, one more topic I want to cover in this whirlwind introduction to the language of Matlab are conditionals. Those are important. So in Matlab, the main one, close to the only one, is the if-else conditional. So you check whether something is true. If it is true, you execute one command, but if that condition was false, then you execute maybe a different command, or maybe you don't execute any command at all. So as a really simple example, suppose we type if 1 equals 2. Okay, a couple things to note here. First of all, notice I used a double equal sign here, because that's the way you check whether something is true. You use a single equal sign when you want to assign a value to a variable, but you use a double equal sign when you're checking whether or not something is true. So a double equal sign for conditionals like this. So we're going to check this stupid condition. We're going to check whether 1 is equal to 2 or not. Presumably it's not. If it is, we will display what? And if it's not, now that's what the else statement introduces, right? The else keyword, I should say, then introduces what to do if the condition that you checked up here was not true, which it's not. Then we'll display no way. End. And the end is the end for the whole if-else statement, right? So if you execute this, it checks this condition, it sees that it's false, so it does not print what? By the way, the disp command in MATLAB is just a way of printing to the workspace there a string, right? So it'll just print the string into the workspace, right? There is a print command in MATLAB, but it's used for printing. I think I recall it's used for printing graphs, right, or graphs of functions and things like that. So images. So if this condition was not true, which it's not, then it should print no way. So if you execute this, type this in and execute it, it does in fact print no way, as expected. As just a slightly more complicated example, let's say that x equals 1, y equals 2. We'll just set those values up initially, and then we'll check to see if x is less than y. If so, we will print the less than sign. If this is false, right? And for different values of x and y, it might turn out to be false, right? Then we'll go on and we'll check another condition. So that's what the else if command is for. If the first condition failed, you have the option of checking a second condition using the else if command or keyword, right? So this will now check whether or not x is equal to y. In that case, it will print out the equal sign. And then finally, else. So this says if neither of those two conditions that we checked were true, then it goes to the else keyword and it'll type greater than, right? Because that's the only possibility left. Assuming x and y were real numbers, right? Then the only possibility left is that x must actually be greater than y. And again, you type this in and execute it. It prints out the equals command as expected. You can try it with different values of x and y. It should always print out the appropriate thing, right, depending on which of these conditions was triggered. So you can use this if statement to simulate rolling a fair six-sided die, using the rand function to generate a random number and then checking some conditions, right? This is not the easiest way to simulate rolling a die, but it works, and it's just a demonstration of using the if statement with a series of conditions. So what we could do is we could first of all generate a random number, and again the rand function generates a random number between 0 and 1, and we set that equal to the variable r. Okay, so r contains this random number. Now we check, is r less than 1/6? Well, that would be, we could imagine that would be like the lowest number you can roll, so that would be like a 1. We'll display a 1 in that case. If that is not true, then we go on, we check a second condition, we check is it less than 2/6? By the way, if it failed, if the first condition failed, that means r was not less than 1/6, so it must have been greater than or equal to 1/6. And then if the second condition is true, that means in fact r must be between 1/6 and 2/6. And therefore we can associate it with the second highest number we could roll, which would be a 2. We'll display that. So then we keep doing this sequence of conditions that we'll check, right? If r was not less than 2/6, then we go on, we check is it less than 3/6, in which case we can assume it represents a 3. And if not, we'll check is it less than 4/6, in which case it represents a 4. And if not, we'll check whether it's less than 5/6. If it's not less than 5/6, then the only possibility left is it must represent the highest number you can roll, which would be a 6. Right? So you can enter this into a script and then execute it. I called the script fair die 6, and every time you execute it, you get a different number between 1 and 6. But it'll be a random number between 1 and 6, right? So this is a way of simulating a die roll in Matlab. Okay, so we did it using this if statement. This is rather ugly, writing out this series of nested conditionals like this, but it works, and it's just a demonstration. I have a problem where I'll ask you to do this in an easier way, simulating a fair die in an easier way by using either the floor or ceiling functions, and then you don't have to use all these conditionals.